that's going to be a nice convex limison. This one here, oh, wimpy outside. It's going to get sucked back in and make a loop. Isn't that fun? That's the way I like to look at it. That's the way Bryce thinks about it. Okay, come on, Bryce. Come on back. So we got our dimples. You got the orientation. What does what? You had some crazy notes in that sheet that you took with you. Well, we're going to summarize them in a little bit different way. If you were a limison person and you went back to your table, stupid thing, come back. You guys had this, the idea of, in this particular situation, of those limisons. By the way, I'm down at the bottom again with limisons. This is the limison. We talked about this as being r equals a plus b cosine of theta. Now the only difference between that and sine of theta is orientation. This has x-axis symmetry. That's what the cosine. X-axis symmetry. I can't write this. Let's try it that way. That's x-axis symmetry. That's what the cosine determines. The a and the b, you guys had this ratio business. I'll convert it and you'll see what happened in what I explained a minute ago. But your sheet said, all right, this limison has a loop when, and I think it said a over b, I'm reading it off the sheet, is less than 1. Well, I don't like reading it like that. I prefer to multiply both sides by b. I think of it as a less than b. Same expression. Multiply both sides by b. You can choose either one of them, however you want to think about it. When a is less than b, we get a loop. Remember this power, the force field, or the gravity of this one is overcome by the b, and so we get a loop. It sucks it back in. But if I do, I get a cardioid, which is a dimple. It looks like a heart, has a little dimple. The cardioid happens when the ratio of a to b is 1. If I multiply both sides by b, I could represent it as just a equals b. Same idea. And we found that when they're equal powered, it touched at the origin. C, if you had, now this one's a little more detailed. You had a dimpled limison. It's dimpled. Now that's like, it's a less dramatic, it's not the cusp you get from the cardioid at the origin. By the way, I'm going to put in here touches origin. That's important because a cardioid does and a dimpled limison does not. So, not touch origin. And feel free to turn your desks. You guys get comfy. Don't you feel like those are glued or anything? This is what's written in your sheet.
Where is this?
It's not on your notes. It's from a sheet you guys had on Friday. And so I'm writing it up now for your notes. So Jackson, this is key. This is the stuff. This is what we just summarized by looking at those graphs, and so I'm putting it in a short form. There was a form of it from Friday, but I'm going to convert it for your benefit. So y'all remember, you're getting that. You're those old grown-up folks now that you just say, I think I need to know this, so I'm going to write it wherever I can. Wherever I can. So b times 1, if I multiply out the b like I did on the others, which is fine, remember in a multiple inequality I have to multiply all parts by b, so that would be b less than a less than 2. It just means b is less than a. It stands for this right here. This is the expression I'm working with. Top here.
What does A say?
A?
Yeah.
Well, A, I'm just, remember, okay.
No, like,
Part A? Loop.
yeah.
There's a
That's
loop. Yep. Did you think it was something else?
I did not even know it was.
Loop. So we're dealing with loops, we're dealing with cardioids, limisons, dimpled limisons, and convex limisons. We're in the dimpled one now. If I multiply through by b, I get b is less than a. We figured this out. Remember we got a dimple whenever the b was less than a? Okay, that's like this red one here, or actually this one's better, the black one. B is less than a, we get a dimple. Okay, so anytime b is less than a. Now, there's a limit on this. The last one, the red one on there, is actually what's called a convex limison. Because there's a dimpled limison becomes a convex limison when the A to B ratio gets to 2. And I'll show you that right now. Check this out. So convex is just a a breakpoint. Dimpled is, you're good. You're dimpled as long as B is less than A, but I'm sorry, this should be 2B on this side. Do you see that B? This B is not happening. Can you see that B right there? 2B is what's supposed to be written right there. Let's make it look 2B. 2B. So when B is less than A, but still less than double B, that's when you get the dimpled. On your notes here, it says A over B greater than or equal to 2 if you multiply both sides by B. If I get A greater than or equal to 2B, okay, then it becomes convex. If I go back to my crazy picture here of the red circle, or the red limacon, check it out, check it out, check it out. That A term is twice as big as the B term, and as soon as that happens, or the ratio gets even bigger, it becomes a convex limacon. Here's the story on the convex limacon. It's hard to know what it is. It looks like if you lay an orange on a table for a long period of time during a day, it starts out perky and round. But if you lay an orange on a table and let it sit there all day, it'll have a little flatness on one of its sides. That's a convex limacon. Now the other version that I'm most familiar with is babies. If you lay a baby and they sleep on their back for extended periods of time, all our Sealy babies were back sleepers with their head back, arms up like this. And their heads got really flat in the back. In babies, their heads have not formed, all their plates have not fused, and so they're really soft, and so they actually get flat. And some people have babies that sleep on their side all the time, and they get misshapen sides of their head, so they're flat on the side of their head like this. Don't look at me so closely. I'm not telling you, but anyway, laying on one side, if it's all squished, it can happen. So what they tell you with babies is you have to flip your baby. So just every now and then you have to go over and turn your baby over so that you make sure that your baby doesn't get a squished side of the head. And they're on their back, they get a little flat, so I tend to like to roll them around. And the flat's not so bad because eventually they just flip over and they just don't worry about the back of their head anymore. So Danny and Bryce, laying on that side, you guys should probably turn because I know your brains are still fusing. And I don't want you guys becoming convex limacons with some kind of depression on the side of your head. Uh-huh. Right. So limacons these are the characteristics we found out. These are graphs. Bam, 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 bam. The ratio is, think of that lead number, sucks it out. If the lead thing has a gravity equal to the gravity there, it touches at the origin. Greater gravity, it pulls it out to a dimple. Even larger, double or more, it pulls it out to what's just a little flattening that happens like with the baby's head. And then if it has a wimpy old gravity on the outside, that thing sucks back in and makes a loop on the inside. Now that's the beginning of the story. Okay, so down below, I gotta find this thing. Good so far?
How do you translate?
What's that?
How do you translate?
Oh, we'll flip those around if we need to. Now here's the question at the top. It says find the maximum R value. I gotta write this on here. Your maximum radius is A plus B. Your minimum radius, and let's look at what that means. It's not like when we do a rose curve. The radius is the length of the petals we think of. The maximum radius is all we have. I like to think it's just the absolute value of those. So in this, the minimum radius, 2 minus 2 in this example, I'm going to go to the others and just remember maximum is the sum of those two values, the minimum is the difference between those two. I'm not worried about sign at this point. But take a look and see how this works out. In the orange graph, the maximum radius would be 4. So if you look at the orange graph, it goes all the way out to 4 on the one end. The minimum radius is 0, and you notice it touches at the origin. On the black graph, the maximum radius would be the sum of 3 and 2 is 5. There it is. The minimum radius is the difference between those, which is 1. And look how far apart that little dimple is from the origin. 1 unit. So that difference, how far your small distance is from the origin, that's your minimum. How far the large distance is from the origin is your maximum radius. Down below in the red one, 4 plus 2 is 6. That's your big radius, up to 6. Our little radius is the difference between the two is 2. Nice. Okay, so those are the radii. Onward. Next big slide. Now, identify the points in the graph of 3 cosine 2 theta that give maximum values. I'm going to slip back up to the top of your sheet now. So I'm going to abandon these notes that I got were kind of in a wacky order. So I'm paving my own way. So we're going to go with the roses. Okay, from Briarwood. Here goes. 1. R equals 2 sine 3 theta. Do you know where I'm at now? And 2, go find these graphs. R equals 4 cosine 4 theta. You got it? You found it? Okay. If we go by Sydney's description here, how many petals are we going to have? Petals. 3. Okay. This is the form of a rose function. It's a sine n theta with symmetry about the, this is a vertical, so it's y-axis. So y-axis symmetry. That's one option. And if you have y equal, or what am I saying, y? R in both cases. If r equals a cosine of theta, or n theta, then you have x-axis symmetry. So we have the general idea of what the graph looks like. Petals 3, and the next piece would be your max radius. We're interested in that max radius, also known as petal length. We're interested in that. In this case, it's going to be, golly, I can't get that right. It's 2. That A is going to be your petal length. So keep that in mind. Petal length all the way around. Petal length. All right, make sure you can read that, Taylor, because I know that means petal length for A.
Gotcha.
Got it. I just know you'll find and help me point those out. All right, here's the next piece. Trace. We're going to fill this in for both of these. By the way, I'm going to look at the next one. Trace is in. I want to know how long it takes to trace this out. So grab your calculator, and we're going to do 2 sine of 3 theta. It works, really only works on the graphing calculator. So this is perfect, because you get to do some graphage. We're going to finish just in time. 2 sine of 3 theta. You have to go mode polar. I'm going to show you some other cool stuff really pretty fast. So grab a calculator, because I will show you a few new things, even if you think you know it all. Polar is the mode. You go to y equals, it's not y equals anymore. I put in there 2 sine of 3 theta. And you can graph it like in, if you go zoom 6, that's fine. But it'll be kind of a small looking graph, like you can't check it out. It's too small. Even that one didn't go very well. Zoom. Square, I think, is my favorite one. So I'll let you guys catch up. Ugh, lag, 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 lag. 5. Thank you. Hey, graph, where'd you go? I didn't turn it on. Helps when you do. There you go. So I did zoom square, really tiny. So generally the window, I know you know the radius of this thing is 2. So just make your window kind of fit. I'm going to make my radius, I'm going to go at least -3 to 3 on all my dimensions. The window is still in terms of x and y, if you notice, and so I'm just going to put -3 to 3 to box in my left and right, and -3 to 3 to box in my up and down. That'll be big enough, and there's my pretty limit, or my pretty rows. So 2 sine of 3 theta. And I changed my window to go from -3 to 3 on all directions because I knew my radius was 2. That being said, I want to trace. I need a counter. Who's a really good counter?